Thank you very much. Thank you for inviting me. So this work is part of a larger project I've been doing with Arieh Iserles. He was my PhD supervisor, but this work happened started about a year after my PhD was finished. But this part of the project we've been working with Karen Luong, who is a PhD student here at Cambridge. I'll get started. So the basis that I've been interested in here is called the Malmquist-Takenaka basis. It's a rational function basis with prescribed poles. So for n as a positive integer, you see you've got a n plus first order pole at I over 2. And then we also have negative n as well. So it's indexed where the pole will be on the complex conjugate. Now this basis has a lot of history actually. I'm not sure how many people have seen this thing before. It goes back to the work of Malmquist and Takenaka for pure mathematical reasons, and it was later picked up by Walsh. But then since then it's found more applications in things like signal processing and spectral methods, because it has quite a few remarkable properties. So some of the names on here people will have heard of, and some of them are in the room. Boyd and Weideman is in the room. He has quite a few papers working on this. Xian Olver has done a little bit of work because these functions are eigenfunctions of the Hilbert transform. And also today, Andrew Horning mentioned that in his work with Alex Townsend and Matt Colebrook, they've been using this basis with great effect. Now, it can be generalized so that you can insert a complex number lambda to choose where this fixed pole will be. So you'll have fixed poles at either lambda or lambda conjugate. And different people will use different conventions as to where you choose the poles. But we like to choose I over 2 to be the pole, and you'll see why. So now, the first comment is what's really interesting about this basis. If you have an x being real, then this quantity up here obviously has absolute value 1. So it suggests do a change of variables e to the I theta equals that quotient, and then there's a easy to compute inverse transform, x equals a half tan theta over 2. So this quotient appeared in the rational function. So if you just pull out the one linear factor on this denominator, you'll see that we've got that term of absolute value 1 to the power n. And so essentially these functions can be mapped to the Fourier basis. And the expansion coefficients in this orthonormal basis for a function f, given by this integral because it's an orthonormal basis, are actually Fourier coefficients of this modified function. So you can compute the first n coefficients in this basis using the FFT. Quite a nice property. Yeah. Another remarkable property of this basis is to do with the Laguerre polynomials. So they're orthonormal with respect to this exponential weight on the half line. And I think it's due to Wiener that the inverse Fourier transform of these guys, these Laguerre polynomials, when you weight them by the square root of their weight, so there's a xi over 2 there, you get these rational orthogonal functions. And because these functions are an orthonormal basis on the half line, we've taken a Fourier transform. Parseval identity says that the resulting functions are orthonormal as well. And if you want to get a complete orthonormal basis, you have to extend not only from n and positive integers, also take the whole of z, or z. And the remarkable properties just keep going. So they have highly structured differentiation matrices, which is where Arieh, Iserles, and I first rediscovered this basis. And these properties, I believe, were discovered by Christov in 1982. So they have a extremely sparse and skew-Hermitian differentiation relationship. They're the products of two basis elements, and also with a modified basis element, have very sparse representations that are structured. So if you discretize a variable coefficient in a ODE, you would get a Toeplitz bus. You would get Hankel operators here, or yeah, you get Hankel operators. And this is reminiscent of the Olver-Townsend spectral method, with highly structured differentiation matrices and highly structured variable coefficient discretizations. Except this is on the real line. This is the basis on the real line. And as I mentioned before, these guys are eigenfunctions of the Hilbert transform on the real line. So Andre Weideman had great success with this basis for the Benjamin-Ono equation, which involves the Hilbert transform. And what do they look like, these rational functions? They look like this. They've got, well, I've plotted the real and imaginary parts in blue and red for various indices. They look like a basis. You know, they oscillate faster and faster as you increase the degree. And the lingering question is always, what are the approximation properties of this basis? I've shown you all these nice properties, but how does it approximate functions very well? Is it actually going to be useful as a basis? Okay, let's look at some examples. If this is a rational orthogonal basis, can it approximate a rational function well? Yes or no? So these are the expansion coefficients for approximating this function, and they decay geometrically. Quite nice. So recall that it is indexed by all integers in all positive and negative integers. That's why there's negative indices on the x-axis. Okay, what about if I take a slightly higher order rational function? Let's make it a teeny bit harder. You might think you might think there will be problems because the basis decays like 1 over x at infinity, but I'm making it decay much faster. So you think that that might be problematic, but not really. It decays at exactly the same rate for this particular function. Okay, and what about if I multiply by cos x? Just made it a little bit wiggly. Should have a similar result, right? Is it going to be faster, slower? Way slower. It's a very surprising figure that we just multiply by cos x, and then this whole exponential convergence goes away. Well, this is not good.
Can I ask about the first two?
Yes.
If you change their scale, in other words, put a factor in front of the x squared, what happens?
Then the rate would change, yes. So I've chosen this because the poles are in the same location. You'll see on the next slide that that there is a Bernstein type theory about analyticity in certain regions. Okay, but there's a real mystery here. Why has cos x messed everything up? It's got the same poles as I was just discussing. Well, I think Boyd solved this problem, and Weideman also wrote about this in one of his papers. Recall that these coefficients in this basis are just Fourier coefficients of a modified function. So if you use the standard convergence theory for Fourier series, or equivalently Laurent series, you get different rates of exponential convergence for Laurent series if you are analytic in various annuli. So how big this annuli can be taken closer to 0, and how big this can be taken out to infinity surrounding the unit circle, which is sort of where the Laurent basis lives in a sense. If you just transplant that result, you get the following, that you'll get an exponential rate of convergence for the coefficients with the exponent rho. So if and only if this slightly modified function, where I've just multiplied by 1 minus 2iz, can be analytically continued to the complement of two disks. So there's a disk with the center A rho, which is this center here and here. and this radius in terms of rho. So it's just this annulus gets mapped to this dark region here. And the key thing is that it actually includes infinity, includes the point on the top of the Riemann sphere. And also, if your function is going to be analytic there, if this function is going to be analytic there, surely f must tend to 0 as z tends to infinity. So that sort of explains, well, not even sort of, that explains why you don't get convergence for this function. As x tends to I times infinity, it blows up exponentially fast. So you're not going to get exponential convergence. That's that. It's sounding like bad news. But Weideman did a little bit more work, because once you actually look at it in practice, it doesn't seem so bad. So for example, e to the minus ix squared, you don't get exponential convergence because it clearly blows up as you go up in the complex plane, quadratically exponentially fast. Sounds really bad, but no, you get fractional exponential convergence. And for the hyperbolic secant function, you'll get root exponential convergence. And Weideman found these by steepest descent in the complex plane, which I'll explain a bit more. But it's not all that bad. So the in-between result is that if your function is, I'll save it for later. Let's not get ahead of myself. So this is e to the minus x squared. This is a plot of the coefficients. It's not exponential, but it's not bad. If you shifted it over, which is always a worry, it gets a little bit worse. If you're working with a Hermite basis, for example, then you can have real trouble here, because the Hermite basis is flat outside of a certain region. But because the Malmquist-Takenaka basis only decays like 1 over x, that effect is not as pronounced. So you can still shift outside the region where your basis is supported. Now, what if I multiply by cos 20x? Experience from the previous slide says this is going to be bad, but not really. So there's some mysteries. I suppose they're not too mysterious, but there's some mysteries to be solved about what is going on with the approximation properties of this basis. So what we've done in this project is focused on a certain class of functions, wave packets. So cos omega x times by a Gaussian type function. Think of quantum mechanics as typical solutions of Schrödinger equation, and wave packets are important there. But we just want to get a handle on what more can we glean about the approximation properties of this basis. And we had these two figures that we wanted to explain. The first one on the left is, as you increase the frequency omega, the number of coefficients you need to get a desired accuracy only grows linearly. Can we explain that? And also, if you look on the right figure, I plotted the coefficients for various frequencies of this wave packet. And as you increase omega, there appears to be a certain shape. What is the shape of these lines for large omega? We just want to understand what's going on. Okay, and if I just don't use cos omega x, I use e to the I omega x, then what happens there? Well, it's actually a simplification, because all of the coefficients for n negative, going back here, for moderately sized omega, they're very small, and we can explain that. But then, at some certain critical point, so you see, as I vary omega, there's a peak that appears at different points, where then, from then on, the convergence begins. So there's some interesting behavior. Can we explain that? Turns out we can. What is this critical value of n, where the convergence kicks in? Because that's the minimum number of coefficients we're going to need. That will give us a lower bound. And I mentioned that André Weideman had used the method of steepest descent in the complex plane with some success. So I'll just quickly explain it, although there were some talks yesterday which taught in depth about numerical steepest descent in the complex plane. So if you've got an integral of this form at the top, and h is an entire function, then you can deform the contour if you're being careful. And you'll still have the same value for the integral. And it's at stationary points where the derivative of h is 0, where you can make a local expansion of your function. So if you have z0 where h prime is 0, h of z can be approximated locally by this quadratic expression. This term pulls out of the integral to come here, and then this is a scaled Gaussian. And this suggests a completely localized approximation to the integral. That's the key thing, is that you can, in some cases, turn an integral over the whole real line into a completely localized expression, particularly for oscillatory integrals. And these coefficients for a wave packet very easily turn into a function of this form. So if I express this 1 plus 2ix to the n as e to the log n times by this guy, and then this numerator becomes this e to this expression, then I've got it in the desired form. This is following what Andre Weideman did. But you will also have a symmetry condition, which allows us to reduce it to the real part of an integral over the half line, which makes things a bit simple. However, usually with oscillatory integrals, you have one variable which are taking, one parameter which are taking very large, which increases the oscillation. But here we have two variables. We have omega, the frequency of the wave packet, and n, the degree of the basis element for which the coefficient is of. So we have to be careful. We have two variables going on. It's definitely not the case which we can do with our eyes closed and our hands behind our back. Okay, well, compute the derivative. And thankfully, it's a multiple of a cubic in z. So this is the most ideal case you could possibly imagine for finding saddle points for steepest descent in the complex plane. We can use the trick of Cardano all the way from 1545 to find the exact saddle points for this integral, albeit with a complicated formula. It's quite an experience to become familiar with cubics. Such a pointless exercise, but yeah, we have them exactly. And here is where we start to see we might need to be careful, because this lambda n omega, and I haven't mentioned that mu n omega is the same thing but with a minus in front of the square root. We start to see that we have to be careful, because omega cubed is the dominant term here, unless n gets bigger than order n omega cubed, which is not the regime we're thinking of. So if we were to just fix omega and take n really large, asymptotics would only really kick in when n got to omega cubed. But we've observed that we only need a linear number of coefficients in omega. So we're starting to see that we need to be careful. Okay, but what do these saddle points look like? Well, there are three of them. It was the roots of a cubic. And what I've plotted here, well, actually, I think Karen did this plot. Let's give her credit. That there's one root which is always imaginary, and the path is what happens as n increases for a fixed omega. So for small n, these two other roots are imaginary and are on the imaginary axis, and this guy always stays imaginary. But at some critical n, you might have heard that phrase before, at some critical n, these saddle points leave the imaginary axis and go out into the complex plane. And that critical n is where we have that turning point in the coefficients. So this method of steepest descent predicts that. And on the top right, the orange lines are the paths of steepest descent. It looks worrying because it looks like they're just going off to infinity, not in the right direction. But actually, if you zoom out, the path of steepest descent goes from the poles of the Malmquist-Takenaka basis through the saddle point and eventually converges to an imaginary part omega over 2. So they're not getting far away from the real line. So not computationally, but for the purposes of the proof, this is a schematic the contour will take, which modifies the original contour of simply 0 to infinity in a simple way. And this is exactly following the suggested approach of the work of Henri Weideman, which was when omega was 0, that this combinatorial distribution turns out to be 0, this turns out to be negligible, this one too, as you take a limit, and this one negligible as well. And yeah, the exact formula reveals that the actual critical point of n is omega over 4. Now, we know this approximation exactly. We know the roots exactly, and we know the steepest descent approximation is written in terms of g and g prime prime. And so what I've plotted here is the coefficients in omega for the Gaussian case, and then the approximation given by method of steepest descent, and it fits incredibly well. And then the critical point here is actually minus a half, I think. Yeah, I've missed that, minus a half. Increasing omega here, you see that the method of steepest descent is a good approximation. We're not kidding ourselves. Okay, but what is this red curve? It's some complicated thing in terms of arctan and these roots of a cubic. It fits. What is it? And the only way we've been able to get a handle on it is to look at it in the following way. So define the quotient of n plus a half and omega, call it c, and then we start to expand these terms in the roots. We have to assume that this constant c remains bounded. We're allowed to take omega really large, but the n's have to be within a constant multiple of omega, essentially. This is the regime. I mean, you can usually with asymptotic studies like this, you would fix the ratio and then you would take omega to infinity. And you can do that here, but our asymptotics are valid for a range of n, and we'll take basically it's the range where this quotient is greater than a quarter, which corresponds to n being bigger than the critical value. And also it's just bounded above by a constant. And when you do that, we get an asymptotic expansion, and hiding in this big O is this constant, which we're assuming is bounded. So if you don't assume it's bounded, you're going to have trouble. And I'm not expecting you to follow what we're doing, but I'm just showing that it's very simple expansions once you make this assumption. So it took us a while to just find out what was the right assumption to make everything fall out. And we get a nice, simple expression for what the saddle point of interest is in terms of large omega. So just to recap, we have an integral of this form where the phase function g is given here. Our regime is we assume that this Cn omega is bounded between a quarter and some constant c, and we're letting omega get really large. And then we get an expression for the saddle point. And after doing more heroic algebra, we get a nice formula which says the coefficients in this regime, which is just the initial regime for large omega, look like exponential convergence in n times by some bounded oscillatory term. And as omega gets bigger, the rate of convergence gets worse linearly. So the next slides will show that we're not crazy and that this is accurate. But what it says is that it explains that the coefficients are going to get more and more straight in their convergence. It's going to be more like straight lines as omega gets large. which is what we do observe. Furthermore, that the number of coefficients needed for any given accuracy will be proportional to omega. But it's not exponential convergence. Remember that you needed to be analytic at infinity. You needed to actually also tend to 0 at infinity, but these functions don't do that. Yet we have this transient exponential convergence. Okay, so this is a plot of the coefficients in blue for omega equals 1. And then our approximation is in red. It's terrible. They don't match. But as you increase omega, this is omega equals 10, 20, 40. We're getting this is omega equals 10,000. Basically, our approximation at the top is not crazy. Although there are some real things to get your head around with regards to the assumption that we've made about where our expansion is valid. So the expansion is valid initially, so it seems to be more valid here than it is down here. That's consistent with our assumption that the big O in front of the negative powers of omega, that contains things which depend on how big this the ratio between n and n plus a half and omega was. Okay, so to summarize, these Malmquist-Takenaka functions have a long history due to their remarkable properties, I suppose. And their approximation theory, which is what we're interested in today, was pioneered by Boyd and Weideman in the 80s and 90s independently. And part of some of the work they did, they showed that you will only get exponential convergence if, but not only, if the function tends to 0 at infinity in all directions, and it's analytic at the top of the Riemann sphere, which is a strong condition which suggests this is going to be a useless basis. However, I've not written down a wave packet correctly. There's supposed to be a e to the minus x squared. Oh well, something like that. We've shown that we need order omega coefficients for any given accuracy. Although this talk was only a sketch of that. And we showed that there's a transient exponential convergence for large omega. There's a paper that's currently in preparation. We'll see how long it'll drag out. Hopefully it's going to be faster than when we were working out what assumptions we could make on n and omega. And future directions is to see how modifying the wave packet, shifting it from left to right and spreading it out, how that will affect the convergence. And it's sort of working towards a more general approximation theory. Is it going to be possible to have, for example, a theory like the exponential rate of convergence for Chebyshev approximation is based on how big of an ellipse you're analytic in. Can we get something like that for this basis? That would be interesting to see, and might explain some of its success. And really, this is for us about spectral methods on the real line, and it's still a question to us whether there are any real advantages to doing it on the real line over simply truncating the domain. That remains to be seen. I'll stop there. Thank you.
One quick question before we go to something.
Cool.
I'm amazed that John hasn't said that exponential can be written down and go on across the book. Yes, I haven't said that.
There's another remark I might make. With your balance between omega and n, it's just a method of dominant balance or something. In your exponent, you're putting them both at the same order of magnitude.
Yes.
So one would expect in general ground. You're balancing as many possible terms in order. So one would expect that ratio to come in.
Okay, I've never heard of that. I'm not an expert in that sort of stuff. Can I pick your brain about it later? Is that all right?
I don't recognise it from where we've got it either, but it probably is in there in a certain sense.
Yeah, because we were fumbling about with it for quite a while. Because, yeah, I could if you just fix omega and let n tend to infinity, as I said, you get sort of really these are exercises. You see that the purple line gets worse and worse for larger omega, and the green line, which is what we finally got gets better and better. So we were really naive at the start.
The point of Stefan's remark is there's a great deal known about this from diffraction theory.
Really?
Lots
Okay.
about, relating to neighbouring branch points and neighbouring singularities. And you get various canonical forms. And I would think some of what you've done could be placed within that framework.
Right.
I'll show
Okay.
you afterwards.
Okay, yes, please.